Okay, welcome to 6.3 Notes. Today's learning objective is to prove triangles similar using a variety of postulates and theorems. So the first thing that we're going to talk about here is triangle similarity through angle-angle similarity. The basic idea here is if two triangles are similar if two pairs of corresponding angles are congruent. Prior to this, we had learned that similarity meant that two figures had some corresponding congruent angles and proportionate corresponding sides. Here, this postulate will allow us to kind of go around the side lengths and say if we have two pairs of corresponding angles that are congruent, we can automatically say that we have similar triangles. So before we go through this example, we are going to talk about the angle-angle similarity theorem, the angle-angle similarity postulate, which we added to our on our geometry reference page. So we'll see here on the reference page we've added this similarity postulate for AA, which is angle-angle. If two angles of one triangle are congruent to two angles of another triangle, then the two triangles are similar. And we can see here that we have triangle ABC and DEF. Angle A and angle D are congruent. Angle B and angle E are congruent. And therefore, we can say that triangle ABC is similar to triangle DEF. So back on the notes now, we are going to talk about angle-angle similarity and how we use that to determine if triangles are similar. And then if they are, we'll write a similarity statement and explain our reasoning. So here we have angle EDC is congruent to angle HGK because right angles are congruent. So all right angles are congruent to one another. So we already have one pair of congruent corresponding angles. Now we're given here that this is 64 degrees, and we're given here that this is 26. So we either needed to find angle E or angle K and show that they were equal and then congruent through the definition of congruent angles. So we chose to do angle E. We used triangle sum here to find the measure of angle DEC, just angle E here. So we took 180 minus 90 minus 26, and that gave us 64. And that's what we see right here. Now, because it was 64, and because angle H is also 64, they have equal measures. They are therefore congruent through the definition of congruent angles. So we can say then that triangle DEC is similar to triangle GHK. Our explanation would be angle-angle similarity because we have one pair of congruent angles and two pairs of congruent angles. So we really only need two pieces of information to prove that our triangles are similar. We can see that here in the next example. We want to prove that triangle ABE is similar to triangle ACD. So that's this big triangle is ACD, and then we have ABE is this smaller one. So what we're going to say is first we're going to list what we're given. Well, we're given the measure of angle ABE, and we're given the measure of angle ACD. So those are our given pieces of information. Now if they have the same measures, we can say they're congruent by the definition of congruent angles. So that's one piece of information. That's one pair of congruent angles. Well, here we notice that angle A is in triangle ABE, but it's also in triangle ACD, this big one. So we can say that angle A is congruent to itself through the reflexive property. So now we have one set of congruent angles and two sets of congruent angles, 1 and 2, and that gives us the two angles we need to prove that triangle ABE is similar to triangle ACD through angle-angle similarity. Now on this last example here, on this page, we have triangle SVR, so this one here, is similar to triangle UVT. That's what we want to prove. So first we're going to start with what we're given, and we are given that SR is parallel to UT. These little arrow marks mean that these two lines are parallel. So we start with our given here. Well, if those are given, then we have a transversal here and a transversal here. And if we have two parallel lines and a transversal, we can prove some information about those angle relationships, or those angle pairs. Angle RSV and angle TUV are alternate interior angles, so we can say they're congruent to one another through the alternate interior angles theorem. In order to say that, we needed the fact that these were parallel lines, so we draw our arrow here. Now, just looking at this diagram, we see immediately that we have vertical angles right here. So we can say that angle SVR is congruent to angle TU or TVU because of the vertical angles theorem. So that's an independent piece of information right here. Well, now we have one pair, two pairs of congruent angles, so we can state that SVR is similar to UVT through angle-angle similarity. We want to match and make sure that our corresponding parts line up. So we have the U in the middle here and the S in the middle here. So we have S and U in the same position in each one. We have angle V, so we have V in the same position in each one. So now we'll talk about indirect measurements before we move on to the next theorem. Here we have a flagpole that casts a shadow that's 50 feet long. So here is our beautiful flagpole, and it casts a 50-foot long shadow. And this here represents the sun shining down and hitting it at this angle to create this shadow. Here we have our woman standing here who's 5 foot 4 inches tall, and her shadow is 40 inches long. So we have the same triangle. Now, the triangles are similar through angle-angle similarity, because if we just draw those two triangles where this is our flagpole and that's the shadow, this is our shadow and that's our person, and here's the angle that the sun hits, the sun is going to hit the person and the flagpole at the same angle. So this angle here is congruent to that angle there. They are going to be the same angle. And then we know our right angles are always congruent to one another. Our person is standing up straight. Our flagpole is in the ground at a right angle. So we have angle-angle similarity. Well, if we have similar triangles, we can just use our side proportions, so the ratio of our sides equal to the ratio of our sides, to set up a proportion and solve it. But when we do that, we want to make sure we're comparing the same measure. So we want to use the same units here. So we convert 5 feet 4 inches into inches, which is 64, and we convert 50 feet into inches as 600 inches. And then I set up my proportion. So if these are similar triangles, I know the proportion, the ratio of the flagpole height to the woman height is proportionate or equal to the ratio of the shadow of the flagpole to the shadow of the woman. So I say X inches is to 64 inches, as 50 feet is to 4 inches, which gives me this proportion with all inches as my units. I cross multiply, I get 40x equals 64 times 600, which is 38,400. Divide both sides by 40, and I get x equals 960 inches. And the question asks how tall the flagpole is to the nearest foot, so I'm going to convert that then to feet by dividing by 12, because there are 12 inches in a foot, and I get 80 feet. So that's my answer. The next part of the notes here is going to deal with two other theorems that we can use to prove triangle similarity. On our geometry reference page, we've added both of those theorems here. We have side-side-side similarity theorem and side-angle-side similarity theorem. Side-side-side says if the corresponding side lengths of two triangles are proportional, then the two triangles are similar. So if we can show that the ratio of AB to DE is equal to the ratio of BC to EF, then we can say that these triangles are similar. So we only need, to AC and DF, so we just need those three side lengths to be proportionate. So we need all three, but we only need those three pieces of information. So again, prior to this, we could prove similar triangles by saying all of our angles are congruent and all of our sides are proportional. And then we could solve or say that they're similar if we have two congruent angles. Now we can say it if we just have side lengths. So if we have no angle information at all, if we can at least show that our side lengths are all proportionate, then we can say that our triangles are similar. Side angle side says if an angle of one triangle is congruent to an angle of a second triangle, and the lengths of the including sides, so the sides that make that angle the included angle, so here it would be AB and BC, here it would be DE and EF. So if the side lengths of the including sides are proportional, then the triangles are similar. So here we need two sides and one angle measure, and it has to be the included angle. So if we come back to the notes here, we can do these examples. We're going to show whether this triangle ABC is similar to DEF or GHJ. So we're going to set up the first one we want to know is triangle ABC similar to triangle DEF. So we find the ratio of each corresponding side length. So AB to DE, so I set those up here, BC to EF. It's important that your corresponding sides line up. And AC to DF, I plug in the information I know. AB is 8, DE is 6, and then I have that reduced now to 4 over 3. Both of those divide by 2. I do the same thing here and reduce to 4 over 3. I do the same thing here and reduce to 4 over 3. Because the ratio of each one of those sides is equal, then through side-side-side similarity, my triangles are similar. So yes, triangle ABC is similar to triangle DEF by side-side-side similarity. And it's important to put that SIM here to indicate similarity, otherwise we think you're proving congruence, and we can't do that here. The second part of this question wants to know if a triangle ABC is similar to triangle GHJ. And I do the exact same thing. I set up my corresponding side ratios, plug in my known information, and simplify. So 8 to 8 is 1. But here, 12 to 10 is 6 over 5. I can stop right here and not even have to worry about this one, because I know that 1 is not equal to 6 over 5. Since these two ratios are not the same, well, then I know naturally they're not all three going to be the same. Even if this is 1, or if this is 6 over 5, these two aren't equal. It just takes one set to be unequal. That means that those triangles are not similar. We can also use a little algebra here. We can find the value of x that makes triangle ABC similar to triangle DEF by setting up the ratios as equal and then plugging in the values we have and solving for our unknown. So if we want them to be similar, then the ratios all have to be equal. So 4 over 12, which is AB to DE, has to be equal to the ratio of BC to EF, because those are corresponding parts of the same triangles. So I can set up 4 over 12 equals x minus 1 over 18, cross multiply, divide, and solve for x, and I get 7. So if I found the value of x, then I'm done. Now over here, we see a check. All I've done is plug that value of x into the third ratio, which was AC over DF, to check and make sure I still get simplified down to the same number, and I do. You don't have to do the check in the homework problems, but you can if you would like to verify that your value is still correct. Last, we have triangle similarity through side angle side. Here we have a diagram of a tree with a lean-to built on it. We know that both a measure of angle A and measure of angle F are 53 because that's given to us here. We also know, so we can say that those two angles are congruent. Now we want to know, so we have congruent angles, we want to figure out if our sides are proportionate. And these are our including sides. So FH and AC and AB and FG. That will make these angles here the included angles. So we don't care about GH, we don't care about BC. So we set up those proportions, we solve them down, they reduce to the same thing, so yes, they are similar. And the explanation here, or yes, we could construct it so it's similar, and the reason is by side angle side. Last, down here, we have triangle similarity. We want to know what method we would use. We are going to write a similarity statement as well. Well, we know that angle ACB is congruent to angle ECD through the vertical angles theorem. So here we have angle, we have the included sides, or including sides, so it makes sense here to use side angle side. If we were given two side lengths, naturally we would either want to use side angle side or side side. But it's going to be really difficult to find these missing side lengths. We could write an inequality, but we couldn't get an exact number just with the information we were given. So instead, we set it up with the angles. So we show that those two sides are proportionate. Again, the question doesn't ask us to do that. It just asks us how we would. So we would use side angle side similarity theorem by showing that those including sides are proportionate. And this is the similarity statement we would write. Remember, it's important to line up your corresponding angles. So A to D, E and B, and then angle C and angle C. Let's line up. And that's it.